All right, so today we're going to take a look at the last unit lesson here in the unit, looking at applying quadratics, mainly with some projectile motion problems. So to start, we're just going to try to find the minimum or maximum of this quadratic equation. F of x equals x squared plus 2x minus 8. Just remember f of x, same thing as y. So as we try to find the maximum or minimum, and we see that's in the standard form where we have our ax squared plus bx plus c format. Just remember we want to start by trying to find the axis of symmetry, right, or the x value at the vertex. So to do that, we use that x equals negative b over 2 times a. And look at the values that we have. Currently we have our a values 1, b value positive 2, c values a negative 8. So we're going to have a negative 2 over 2 times 1 gets me a 2. So really, we find our maximum minimum to have an x value of negative 1. From here, all we have to do to find the y value at the vertex is take that x value and go plug it back in. So we're taking this negative 1, plugging it back in both locations for x. We want to make sure we do that in parentheses. So when we look at it, we're going to take and plug in negative 1, close the parentheses squared, plus 2 times negative 1 minus 8. Once we go and plug that into our calculator, with the x value negative 1, we come up with our y value of negative 9. So here we found the vertex. Last step is to figure out if it's a maximum or minimum. So going back to our a value, as long as that a value is positive in front, we know that our u-shape is going to open upwards. So here our vertex is going to be that lowest point, making it a minimum point. Getting into the application problems. We know that we have a formula that helps us calculate the height in feet of an object shot upwards in the air with an initial velocity after t seconds, where h 0 really just represents the starting height or the starting point of the object. So here is our projectile motion equation. So the first part is always staying the same, the negative 16t squared. Next, the v of o really just stands for the initial velocity, or the starting velocity. And then the last one, h, just stands for the starting height of the object. So really just two variables that you plug in there based on the word problem. And then that really gets us our b and c values. The a value stays as the negative 16 in front of the t squared. So if we flip it to the next page, it's asking us to write the equation given the following information. It says a volleyball was hit straight upwards with a velocity of 176 feet per second from a height of 4 feet. So for each of these, we're going to plug it in for, there's our initial velocity. Here's our starting height. So we're going to plug both of those in to that equation. So just remember, here we had like h of t just stands for height after a certain time. Remember, we want to start out with that negative 16t squared. Next would come our velocity in front of t and our starting height. So really we're just plugging in a couple different variables here. We're going to plug in our velocity and our starting height. So when I write out the equation, here it's our height is going to be equal to negative 16t squared plus, we're going to plug in the 176 initial velocity in front of t, and it's at a starting height of 4 feet. So really we just plugged in those two values. And now we're asked to find the maximum height of the volleyball. So since we see that our a value this time is a negative value, we know that our u-shape is going to open up downwards. So really we're trying to find this maximum height, or the highest that the volleyball will go. So nothing more than just trying to find the vertex again. So the first step, we want to try to start with our axis of symmetry to figure out at what time, right, does it reach its maximum height, and then we can plug that in to figure out what that actual maximum height is. So using the values we have, we want to do negative b, or the opposite of b. So in this case, once again, we still have our a, b, and c's in the correct location. So the opposite of my b value would be the negative 176. From there, I want to put it over 2 times a. So if I take a 2 times a negative 16, that's going to get me a negative 32. And then I want to divide those in my calculator to figure out what is negative 176 divided by negative 32. So once I divide negative 176 by negative 32, we end up with 5.5 or 5.5, and that's representing seconds, right? So our x variable in this case is time, right? And the y variable would be height. So now that we know at what time it reaches the highest maximum point, now we just need to plug that 5.5 in for t and come up with the actual height. So here I'm going to write it out where we have our initial equation. So really we're just going back to that original equation we came up with, the one from up top, right? And all we're doing is replacing the time or the t variables with 5.5 seconds. So here I've written it out. Anywhere that I came across and there was a time variable, I'm plugging in 5.5 seconds because we need to figure out what's the height at 5.5 seconds. So now we can type that into our calculator and come up with the maximum height. So once I type that into my calculator, I come up with our maximum height, ends up being at 488 feet. So here, right, height in this case, at least projectile problems, is the y variable. So here at the vertex, we can see that at 5.5 seconds, the volleyball's reached a height of 488 feet, and then it'll start coming downwards from there. So let's take a look at another problem. Flipping the page. Here it says the quadratic equation is used to find the height of a stone thrown upward from a height of 32 feet at a rate of 128 feet per second. So remember, the rate's always the velocity. So here, this 128 feet per second is going to go in for the velocity variable, and then the starting height, in this case, ends up being 32. So we're still trying to plug it into our equation. And then it's asking us how long will it take for the stone to reach its maximum height, and then what is the maximum height. So really, all that's really asking you to do is to find out where that vertex is at, or the highest point in our U-shaped parabola. So once we're trying to find the height, this negative 16t squared part is always going to be there in our projectile motion problems. Next, we're going to plug in our velocity in front of the t variable. Then lastly comes our starting height. So we're plugging in both those values from the information we were given in the word problem. And now we're going to continue that pattern we just did to find our vertex. We want to start by finding the x value of the vertex. So taking the whole opposite of b over 2 times a. So in this case, the opposite of b would be a negative 128. If I took 2 times a, since a is still negative 16, we still end up with negative 32. Then we just want to divide those two things to figure out at what time does it reach that maximum height. So it looks like this comes out to be 4 seconds. So once we figure out our time at 4 seconds, now we're just going to go plug it back in place of the t variable to figure out at what exact height is the stone at 4 seconds after it's been thrown. So we're really, now that we found, just like when we were finding our x, coming up with the y variable, same thing here. So for now we're just dealing with h and t. So we found the time that it reaches the maximum height to be 4 seconds. So we go and plug that 4 back in for our time variable, or t. And then now we can type that in the calculator to figure out what is the maximum height. So no, time was going to be 4 seconds. Reach the maximum height, and then we plug that 4 seconds in for time, we get a maximum height of 288 feet. Okay, one last problem here. Same idea. It says the path of the toy rocket is thrown upward from the ground at a rate of 208 feet per second. It's modeled by this equation where h of x equals negative 16t plus 208, and this should be a t as well, times time. So when will the rocket reach its maximum height, and then what is that maximum height? So here they've already kind of given us the equation here, same equation we've been using. The key here is there is no last value or starting height because it's thrown from the ground, right? So that last value would be a 0. So really, if we had it look just like our other equations, we still have the negative 16t squared. This time the initial height, or the initial velocity is 208, and then the ground level would be 0. So the same process goes to find our time at that maximum height. We want to start by saying opposite of b over 2 times a would give us the time at the vertex. So the opposite of b in this case is a negative 208. 2 times a still is negative 32. So now we just need to divide those things. So after typing in negative 208 divided by negative 32, came up with 6.5 seconds. So 6.5 seconds, it's going to reach the maximum height. So now we just need to go plug that back in for our t variable. So now if I copied it down to try to find our height, we have negative 16, then in parentheses, we're plugging in our 6.5. Close the parentheses before we hit our squared key, plus 208, and then once again, we're going to plug in our 6.5. So we'll, using our calculator, when I go and type this whole right side into my calculator, right, that gets me my maximum height. In this case, I came up with 676 feet. So the process, pretty similar to how we were trying to find the vertex before. Just remember, in any projectile motion problem, since we have the negative 16 as the a value, all of our u-shapes will open up downwards, right? And then really we're just trying to find our maximum height. So we're trying to find the time that it reaches the maximum height and then plug that back in to figure out the height at that time. So the same process as when we were doing. We're just graphing things in standard form. We want to start with that negative b over 2 times a. That'll give us the time at the vertex, and then we can substitute that time back into the original equation to come up with the height at the vertex.